So the initial problem that we're going to consider as a motivation for the idea of a graph and why graphs are important is the Königsberg bridge problem. This is usually historically attributed to Euler, and basically the problem goes like this. Königsberg is a city on some rivers, and there are a couple of islands in the city. We'll call them W, X, Y, and Z. And there are various bridges between these landmasses. There's a bridge 1 and bridge 2 between W and X, bridges 3 and 4 between W and Z, bridge 5 between W and Y, and then bridge 6, X to Y, bridge 7, Y to Z. And Euler's question was, is it possible to traverse each bridge exactly once and end up on the same island we start at? And the idea of graph theory, or mathematical graphs, gives us a way to analyze questions like this one. And so the idea is that we will turn this picture into a more abstract object called a graph, and then talk about properties, mathematical properties that a graph must have. And so the idea of a graph is we're going to have a collection of points that we're going to call vertices and a collection of edges that connect those points. And so in most problems, the vertices are going to represent some objects in our problem, and the edges are going to represent some relationships between them. So in this case, we're going to get a vertex for each island. And then the relationships between the various islands are the bridges that connect them. And usually the way that we draw a graph is we draw dots to represent vertices, and we draw lines to represent edges. So in this case, my graph has 4 vertices, W, X, Y, and Z. And then we have 2 edges between W and X for bridges 1 and 2. 2 edges between W and Z for bridges 3 and 4. An edge from W to Y for bridge 5. And then edges from Y to X and Y to Z for bridges 6 and 7. And this gives us a more abstract way to manipulate the information in the problem. And maybe this makes it a little bit easier to analyze the answer to Euler's problem. And it turns out the answer is no. Because if you think about what happens here, if I pick some point in my graph, let's say I want to start over here at W, then every time that I go to and leave some vertex, I use up 2 of its edges. So entering and leaving a vertex consumes 2 edges. And therefore, any vertex that isn't the one that we start or end at, we have to visit an even number of times. Let's call all of those vertices intermediate vertices. They have to have an even number of edges because we use those edges in pairs. All right, so we could try to continue this path from Y. Let's say I go to Z next. And then maybe I go back to W. But now no matter what I do, I'm stuck, right? If I try to take edge 2 next, then I'll be stuck at X with no more edges to use. If I use edge 5, same thing. If I use edge 3, same thing, getting stuck at X, Y, or Z, respectively, and not using all of the edges. So this fact that all of the intermediate vertices have to have an even number of edges so that we can use them up in pairs as we enter and leave them means that actually in order for Euler's problem to have a solution, for us to be able to start somewhere, use every bridge exactly once, and end up where we started again, every island except for the one we start on has to have an even number of bridges. So this problem is only possible if all but one vertex, all but one island, has an even number of edges, of bridges. But here, if you look at these, at the different vertices here, actually we see that none of them have an even number of edges. This one has 5, this one 3, this one 3, and this one 3. So the problem is not possible.